Okay, so for this second talk of the morning, we're going to have Mikhail Kapranov from the Kavli Institute for Physics and Mathematics of the Universe, and he will be talking about supergeometry.
Thank you very much. I'm not sure if it works. Does it work? Yeah. Well, I would like to thank the organizers for the invitation to speak, which gave me an opportunity to put on paper some of the thoughts I had for a long time. But following the format of the contributions that were proposed, I will start with giving some exposition of how people think about supergeometry. So my talk will have three parts. First, supergeometry as understood by physicists, by mathematicians. Second part is the supergeometry as understood by physicists, because it's a little different, actually quite different. And the third part would be about homotopic underpinnings of supersymmetry, of supergeometry. So let me start with the first part. So for a mathematician, supergeometry is about supermanifolds, superschemes, and stuff like this, which is based on supercommutative algebras. So mathematically, at least we think so, it is about supermanifolds, or superschemes. This is a type of geometry based on supercommutative algebras. Rings of these are geometric objects on which rings of functions are not commutative but supercommutative rings. So I recall the definition of supercommutativity. We have a Zimmer-2 graded algebra. A equals direct sum over I in Zimmer-2. So there are two elements here, 0 and 1, AI. And the condition of supercommutativity is that AB equals -1 to the degree of A, degree of B, that is B. And there is a version of this for Z-grade. So this identity looks like a perturbation of commutativity. One can look at it as a mild non-commutativity. However, the general principle, the guiding line of supergeometry is that it is just as good as commutativity, it's fully good. So that's probably the first principle. How does it go? Let me call this principle of naturality of supers. That supercommutative algebras are fully just as good as commutative. Now, that's why this is so. It's not self-evident. And it's not self-evident a priori, at least it was not self-evident, why we cannot do anything else, anything similar, and go other interesting types of algebra. But what happens is that is more or less the only possibility. So typical examples of supercommutative algebras are like this. First, the exterior algebra. So n variables, which are untaken ci xij equals minus xij I psi I squared equals 0. So we can think that we work over a field K of characteristic non-trivial. This is the exterior algebra, and we can also multiply it with the polynomial algebra. So those are of degree 1. So degree 1. Lambda xi1 xi n, then k x1 xn. That's the second example. No, of course, other examples are the algebras of differential forms, cohomology, and so on. So again, so this formula is in fact a manifestation of the rule that whenever we interchange two objects of different polarity, we acquire a sign. And sometimes this is called the Cazul sign rule. Interchanging. Change of two symbols of parity P and Q should allow a sign -1 to the PQ. So an example of this rule would be like this. Suppose A and B are supercommutative. Then their tensor product, greater tensor product, is also supercommutative. So the tensor product of vector spaces, the grading given by the sum of the degree, but multiplication is given like this: A tensor B times C tensor D. Now this is a definition, that's not an identity. So defined to be -1 to the degree of B, degree of C, AC, tensor DT. And if you do this, then that will hold. So this is sort of, this rule gives some kind of deep compatibility for all the computations. So in fact, when we work with signs, then it is a priori not obvious why we won't get like something equals negative of itself, and then the entire algebra will collapse. So the principle is it will not collapse, and this is remarkable. So a way to explain this a little more would be, I don't know if I should just move the boards, or I'll simply. Let me simply erase this, will be easier. A way of formalizing this principle that I just erased would be like this. So consider the category of supervector spaces. So let S vector be the category of 0 to graded vector spaces. So with graded tensor product, which means the degree of the tensor product is the elements the sum of the degree, and spaces say V, and they introduce the symmetry operation from RVW, from V tensor W to W tensor V, which goes again like this: V tensor W goes into -1 to the degree of V degree of W times R. Then the mathematical statement, again, it is very well known that with this operation, it becomes a symmetric monoidal category. The fact which explains the principle is that S vector and the product and this R is asymmetric. Which means it's just as good as a category of ordinary vector spaces. So therefore, one can consider commutative algebras in this category, and this will give that rule. One can consider Lie algebras in this category. One can consider derivations of commutative algebras in this category, and so on. Yeah. And so on. So they can do basically all the geometry. So, and the concept it leads towards is the concept of a super scheme. So if A is a commutative, is a super commutative algebra, this has the even part and odd part, and this is commutative by itself in the usual sense. So we can consider its the spectrum of A0 is a U-ordinary scheme. And the fact that there is also this thing gives an additional shape of rings. So A1 gives a shape of rings. Or which again 0 to greater, but 0 plus 1, or spec A. And this gives a way of, so we get a ring space, spec A0 or spec A is a locally ringed space. Which we can use such ring space in the same way as they are used in Grothendieck theory of schemes. So, on this kind of Grothendieck type theory of schemes. And similarly, one can do manifolds in the analytic category or smooth category. So in particular, there is a fine space of dimension N, which is a spectrum of lambda psi 1, psi n. There's a C, it's K of S1, Sn. Similarly, okay, C and N. So analytic version. C infinity version. So one can define basically the entire geometry. From mathematically, it's simply because it is a symmetric monoidal category. Now, for a physicist, as far as I could understand, this is not the fundamental object. For physicists, the fundamental concept is supersymmetry, and this appears only as much as it is needed for the purpose. So let me now switch to the second part. So the physical use of supergeometry can be put into the more general framework of some idea of non-observable square roots of everything. Somehow that we should extract square roots out of familiar objects. So let me state this as a kind of vague principle, called principle of square roots. And it simply goes a little bit beyond supergeometry. And it says that it is useful to represent familiar objects, familiar quantities, which may be typically real, often positive and certainly observable, as bilinear combinations of some other more fundamental quantities, which are complex and sometimes not really observable. It's useful to represent familiar quantities. So that positive, real, and so on. That's bilinear combinations. Of some hidden, even more fundamental quantities. Of some hidden, more fundamental ones. So let me start with a list of such examples, which examples don't necessarily have to contain super objects. Probably the first examples would be the wave function in elementary quantum mechanics. So I have a wave function psi of x. It's a complex number, but the value of this complex number cannot be observed. What is observed is the probability density, which is p of x, which is square of the absolute value of psi of x, which is psi bar of x times psi of x. Square. Square, yes. So this is observable, but this is not. And this is positive and real, and this is complex. And there are versions of this. So another example would be example 2 would be the Laplace operator on forms. So we have x manifold, we have the drum complex, so it's a Riemannian manifold. So the Laplace operator is written as delta equals d star plus d star d. So this is self-adjoint, which means a non-negative definite, and this is bosonic in the sense that it has degree 0, and those are fermionic in the sense that they have degree 1. So those more fundamental objects, they often are referred to as fermionic. So in the third example would be, of course, the theory of Spinors as square roots of vectors. So we have a vector space V with quadratic form. The group SOV of rotations, it has a 2-to-1 coupling by the group spin V. So all of this is taking square roots of rotations. And it has fundamental representations. Fundamental representations. Maybe still change the boards. So the property of the spinor representations, as we know, depend on the parity. So fundamental representation, there is one representation of S if D, which is dimension 3, is odd, and two representations, S plus, S minus if D is even. And further properties, they depend on the residue of the dimension and of the signature modulo 8. So it's some further properties. Depend on D 8, which is the version of the bot periodicity. So let me just give two examples, which I'll refer to later. For D equals 4, so there are two representations. So what I want to say that there are, so when I say the spinors are square root vectors, so there are pairings, so bilinear pairings. Or so the Diderot gamma matrices from spinors, pentaspinors, so, and the property exactly how we go, it depends on the residue mod 8. So for instance, for D equals 4, you have a map S plus and the S minus, in fact, is isomorphism to V. And when D equals 10, there will be a map gamma from symmetric square of S plus to V. And similar for S minus. So those are some examples of such square roots. And what's physically interesting is to take square roots also of the translation operators, of the ordinary derivatives, which appears already in this example with the Laplace operator, because the delta is the Hamiltonian, and we want also to take a square root, or as much as possible square root of that Hamiltonian, which is present here. Let me now consider yet another example. Would be let me call it square root of d over dt and delta functions. So the easiest, the simplest supersymmetry would be this operator. Q equals d over d psi plus psi d over dt. So operator in the functions of the exterior algebra on psi, that's a polynomial algebra on t. Or we can take C infinity functions, analytic functions, whatever. So in this algebra, this is a derivation, and we have that if we take a square, which is by the rule, it's 1/2 of the commutator in itself, equals d over dt. So this is closer to the physical idea of supersymmetry. We represent the time translation as a square of something more fundamental. Let me mentioned a relation already of this example. It may seem trivial, but it's related to the point of view on theta functions, which was advocated by Sato some time ago. Sato's point of view. It goes back to 1970s or something like this. But I'll discuss it a little briefly, but I want to emphasize the following phenomenon from fact. Considering the following operator. Consider operator e to the q, which means 1 plus q squared over 2 factorial plus q cubed. 3 factorial plus. And let's look at this operator in analytic functions, in lambda c times O analytic in C. Now, first of all, it converges. So first, converges. And second, it is local. What do I mean it's local? It's word comparing the operator e to the q to the operator e to d over dx, which also converges sort of on analytic functions. So if I write e to d over dt, f t is the summation of the Taylor series. So it's going to be f of t plus 1. So it's defined in a different area, different domain, but f is defined. So when I say local, it means that it's a morphism sheet. So in general, there is a theory of differential operators of infinite order, which also was emphasized by Sato. So let me just say something very briefly here. Suppose I have h of z, with series from 0 to infinity, so a m z to the n. Suppose it's an entire function. Now I want to write h of d over dt. So when local, when it is local. Well, there is an answer. So if the following series k of z, which is sum n factorial a n z to the n, is also still entire. Then h of d over dt is local. This follows from Cauchy formula. It's a rather elementary computation. So if for the exponential function, it's just by splitting by it is not local. But if series decreases even more than the factorials, then it's okay. So in particular, h equals cosine square root of t, square root of z is okay. So and similarly here, this series would be local. So as to not to go too far in this direction, let me maybe say a few. So let me just be a little brief. So I'll just explain where theta functions come into this play. So let's write the theta function, theta of not to script up, theta of t, tx. It was e to the sum over n, e to the n squared t plus nx. So, and when x equals 0, we get the so-called theta null value. So theta t0 equals sum q to the n squared, q equals e to the t. So the interesting question is why this is a modular form. So this is a modular form. So how can we look, how can we see this, knowing only this dependence? And for this, so what I said about this Sato's approach, one can write a system of differential equations of infinite order on this function, which which characterizes it. So satisfies the system of differential equations of infinite order of that kind. And again, to understand this, it is rather elementary, because the theta function, it satisfies the condition of d theta over dt equals d theta d squared theta over dx squared. It's the heat equation. Which means that the differentiation over x acts on this theta function as square root of the derivation in t. D over dx equals square root d over dt. So now, if we write periodicity property of theta function x, it will give us admissible local equations in t. X, well, for instance, I write theta of x plus 2 pi I equals theta of x. Means that I write e to the 2 pi I square root of d over dx, so this of theta equals theta. So if you put that variable q here, we get a differential equation, a local differential equation satisfying this, which it satisfies. And the other periodicity too. It gives a system of two equations. So in this respect, it is kind of cool. What? Yes. I write e to the 2 pi I derivation over x, but if you just use this, we write 2 pi I square root of d over dt. And that's a local equation in t, and one can actually get quite far in this direction.
This is an example of holonomic system.
Yes, it's an example of holonomic system of differential equations of infinite order. But what seems interesting that supersymmetry point of view naturally produces this. You don't have to. It seems to be exactly about this type of thing. So that was an example. I know. So that's an example which is of, so to say, non-relativistic physics, because we just took square root of only d over dt. So let me call the next part. Let's call the square root of space-time translations. Space. So if I just write square root of d over dt, it's not relativistic. So just time is chosen. So to do it better, we should say that we started the vector space V. Now suppose V is our space-time. So what we want to represent like derivations d, v, want to represent as bilinear combinations. So all of them instead of just one. Well, so this leads to the an algebraic construct would be, let's call it a quadratic space. Symmetric gamma from symmetric square of one space V to the space V. Let's call such a datum a quadratic space. So if we have this, then we can construct a superalgebra in which this would be the odd part, this would be the even part. let's call the superalgebra T, I don't know, T, which will be B in the degree 1, would be V in degree 0, and this gamma is the only bracket. So, and such a superalgebra is nilpotent, because if after the bracket we end up in the space which commutes with everything. So it's nilpotent superalgebra. Nilpotent Lie superalgebra. So and it gives by exponentiation a Lie supergroup, so T, corresponding Lie supergroup. And if you consider left invariant vector fields on this T, then they exactly will represent this algebra. So we will realize the different derivatives in V as bilinear combinations of more fundamental derivatives in B. So we can write that T acts on big T by left invariant fields. So we will have vector fields D sub B, and we have vector fields del sub V. So that would be odd, would be usual infinitesimal translations. So we'll have dB commutated to dB prime will be gamma of, would be del gamma of B prime. Well, gamma of BP prime is the image of the product under the map gamma. So in this way we represented, so those are called supercharges. And again, as we had in this example, so those supercharges are of the nature that the exponential of them is local. So E, if I write E to the dB, are local. Even though E to exponential of this is not local. So in practice, for the quadratic space, we take something related to the spinors, will be spinorial quadratic space. So in practice, physical practice. B is certain sum of one or more spinor spaces, the sum of spinor spaces. So for instance, we have S to the power M, to the power E, or S plus to the that times P, some P time plus S minus times Q. So this is referred to N equals P supersymmetry. And this is referred to N equals PQ supersymmetry. So supersymmetry is extension of everything to the action of this bigger group. So plus possibly groups of rotations, group of conformal transformations, and stuff like that, which is kind of old. But this new thing is always like this. It's taking square roots of space-time translations. And only this is really interesting from physical points of view. So everything else is sort of a service material to produce situations in which, or maybe I'll say a little more here. I'll say a little more here. So the supersymmetry is a feature of a theory, so that this big group acts. So supersymmetry feature of physical theory. Which means action of T, or T which is semi-direct product with the spinor group, and something like this. If theory is relativistic, then it should act with this, should be acted upon by V, semi-direct product with SO V, which is the Poincaré group. So here we extend this by allowing square roots of the translations. Okay, so and in the remaining time, I want to move to the third part, which is which I wanted to call the homotopy theoretic underpinning of supergeometry. So it's really remarkable that just by introducing this little sign, the possibility of we extend the commutativity just a little, and so much new things come into the play. It really has no a priori explanation. So it's interesting, therefore, to think a little like what this possibility of extending the signs is related. What it is related with other than this physical theory. So first of all, let's try to understand the signs. Let me call this part the sign skeleton of the causal proof. So this comes from the category of supervector spaces. So we have the category of supervector spaces with the tensor product and the symmetry. This corresponding to Z-mod 2 grading. Or there is a similar version for Z-graded vector spaces. So we perturbed the familiar category of vector spaces by allowing the grading and allowing the signs in the symmetry operator. So let's try to extract the smallest possible skeleton which is responsible for this. So clearly to write this sign, we don't need spaces of high dimension. We just need to write the sign. So enough. So vector spaces of total dimension 1. Which means a one-dimensional space sticking in some degree. Because sign is already there. And also, it's in this category we don't need any morphisms other than isomorphisms, because the sign is an isomorphism. So only isomorphisms. So in this way we get a category kind of which is much smaller, but which retains all the features of the category of superspaces. So let's call this category 1 S vector. So one-dimensional supervector spaces and morphisms are isomorphisms, or one vector Z. So those categories are examples of a concept which is quite known in algebraic geometry and known as and in category theory, the concept of a Picard groupoid. So that of the category Picard groupoid. Picard groupoid, by definition, is a symmetric monoidal category. Category, let's call it P, the tensor product, in which everything is invertible, in which all the morphisms are invertible, which means it's a groupoid, and all the objects are invertible with respect to the tensor product. Therefore, all morphisms and objects invertible. So here, all the one-dimensional vector spaces are invertible with respect to tensor product. We multiply it to dual space and get canonically the field. And all morphisms are isomorphisms because we restricted them so. So in such a Picard groupoid P, we can associate two groups. First of all, group pi 0 of P, also known as the Picard group of P, which is simply a group of objects of P, modular isomorphism, with the operation tensor product. And the group pi 1 of P, which is the automorphism group in P of the unit object, which is canonically identified with automorphism of X for any X. So in our case, we can see what would be the pi 0 and pi 1 of those categories. So one aspect has pi 0 equals 0,2, pi 1 equals k star. And one vector z has pi 0 equals z, pi 1 equals k star. So those categories, they sort of encapsulate the Kazut sign rule. But even so, it is too big, because we only need signs. We only need plus minus 1 here. That's all we need. Only thing we need, so we can cut it down even further. So how can we do this? We should take the field as small as possible, but there is no smallest field. So the best way to do it is to replace field by a ring of integers. So to cut down further, so we replace k by the ring of z. So invertible elements in the ring Z is group of plus minus 1. So we consider, instead of vector spaces, we consider free abelian groups of rank 1 with grading. So we have 1 as ab. Yeah? So free abelian groups of rank 1 with Z-mod 2 grading. And the Kazul sign rule, which we can still write. Or we can write 1 of Z. So then we'll replace it, and we get the real skeletons. And the real skeleton will have pi 0 equals Z-mod 2, pi 1 equals Z-mod 2. And this real skeleton will have pi 0 equals Z, and pi 1 equals Z-mod 2. Now, already here, there is something interesting happens. So we have those Picard groupoids. One can explain the naturality of supers by saying that this Picard groupoid, the lowest one, is in a way the simplest possible and the least restrained. So let me say it like this. Again, it is proposition which is not hard to prove and certainly doesn't pretend any novelty, but it's really appealing. Got the fact that this thing 1RZ is the free Picard point on one object. We can consider one formal object L. So how do we generate a free Picard group point? We can take all formal tensor powers, right? And we take all the morphisms that are needed to write the symmetry. We have R and N from L tensor N. L M to subject to axioms. So if you work out the axioms, we'll get exactly this thing.
No, because L is hot object, the rotation of the corpus is -1.
Yes, that's what I'm saying.
No,
that's what I'm saying.
Hot object.
No. In the concept of Picard group point, there is no a priori order even.
No, but if
No.
symmetric monoidal categories have rotation.
No, we don't require. We don't require it at all. So symmetric monoidal category is simply from A tensor B to B tensor A. And from A tensor A to itself, it can be anything.
Yeah. In this case, it would be -1.
In this case, it would correspond to -1. Yes. Yes, this is the point. R, L, L. From L squared. L squared corresponds to -1. Yes. So that's the point. That we sort of do out of nothing. We can think, what would be the free Picard group point of one object? And so here it is, and everything else is simply a linear envelope. The category of aspect is simply a linear envelope of this. So this is from, if you want, from a philosophical point of view, that's an extremely appealing statement. So we simply have discovered the natural realm of commutativity. Picard group point is an S-commutative object which is S-commutative as possible. And the simplest one, trivial one, precisely gives the Casual sign rule, and well, it gives everything else. So this entire superstructure of physics and mathematics just comes out of studying the free Picard group point on one object. I have time till 12:30. Okay, thank you. So now, if we are into Picard group points, then it is a part of the package of ideas which I think goes to Grothendieck, but I don't know the history fully, that Picard group points, they correspond to objects of homotopy theory called spectra. So let me just say that goes to Grothendieck. It's a part of the his program of pursuing stacks, but applied to stable homotopy theory. Picard points correspond to spectra in the sense of homotopy theory. Spectra with two homotopy groups, only pi 0 and pi 1. And in this correspondence, pi 0 and pi 1 in the homotopy theory sense correspond to pi 0 and pi 1 in that sense. But of course, it's only the beginning of the Grothendieck picture, because there are more general spectra. So general spectra, that's called even 0-1 spectra. So if it has more generally, so if we consider 0 and spectra which have homotopy groups in between 0 and n, they should correspond to Picard n group points, which is a concept which has to be defined. Picard n group points. So basically we have a symmetric monoidal M category in which everything is invertible. So, but of course, if you start doing this, the more and more coherences come up, and it becomes very difficult. But at least the good there is for n, certainly for n equals 1 or 2, that is known. But there is a further inside of Grothendieck. So when we talk about spectra, there is the simplest spectrum, which is the spherical spectrum. And this spherical spectrum is kind of free object. It's an analog of the group Z, analog of the ring Z in homotopy theory. So, and then this dictionary corresponds to saying that the spherical spectrum would correspond to the free Picard n group point in one object. And here we have a truncation. So we have truncation in degrees 0 n of S. So or we can do no truncation and say we have Picard infinity group points that would correspond to the spherical spectrum itself. So then it's even more remarkable that when we do supergeometry, we study the first two levels, 0th and first level of the spherical spectrum. So the homotopy groups of the spherical spectrum are stable homotopy groups of spheres. So pi I of S have a stable pi I stable homotopy groups. So in particular, so those two groups up there are the first two stable homotopy groups of spheres. So let me just write it sort of briefly like this. So for I equals 0, I have, it would be pi 1, pi I stable, 0, 1, 2, 3, and so on. So here the groups will be Z mod 2, the next will be again Z mod 2, and the next will be Z mod 24, and then it goes, which is a remarkable sequence of groups. And it's also useful to compare this with the algebraic K groups of the field K. Ki of the field K would be Z, would be K star. So notice this K star is exactly that one which we got halfway. It's the first algebraic K group. So here, let me just say that a K2 of the real numbers maps into Z mod 2, and this has something to do with spin. Yes? So this has something to do with the signs of permutations. So this is the determinant, sign of permutation. And this corresponds to the dimension, or cardinality. Well, in this something it is related to various string type. Let me just say string mathematics. Such as, for instance, so all appears and things that appear in theory of elliptic curves, but this 24th root of unity related to the transformation of this, or the Euler characteristic of K3 24, and so on. So what happens here, that usual supergeometry, it utilizes only those two things. So usual supergeometry. Now in the physics usage, not just this is utilized, because the spinors, we use spinors. And this is the next level. So let me just say a few things to finish. So mathematical supergeometry. Supergeometry uses zero stable on one side. The physical supergeometry. So also uses pi 2 stable because of the relation between spin and statistics. So statistics is here and spin is here. So in fact, there is something in the structure of the spherical spectrum which is a poor man or poor mathematician's version of the spin statistics theory. I don't pretend to understand that theory, but there is a mathematical statement here, just about the structure of the spectrum. So we have this truncation with homotopy groups being Z and Z mod 2. And we have this truncation with homotopy groups being Z mod 2 and Z mod 2. We can truncate and then take the loop space and get another Picard group point from this and this, with pi 0 being Z mod 2 and pi 1 being Z mod 2. So now that the fact, which is one of the coincidences which make physics work, that this group point is just a reduction mod 2 of this Picard group point. And this is used implicitly all the time in physics. So let me call it like this, a homotopy theoretic. Homotopy theoretic. Spin statistics theory. So the Picard group point. Let me just use the notation. I write here tau 1, 2. I truncate it in degrees from 1 to 2 of S. And take the loop space here. So is identified to the reduction mod 2 to tau 0, 1 S mod 2. So this simply means from the language of homotopy theory that the way this is linked here is the same as the way it's linked here. It's linked by the same Cazul sign rule. So the linkage given by the Cazul rule. And here is the same rule. It's not hard to prove it from the known information about stable homotopy groups of spheres. But this is what makes physical dipping into pi 2 stable consistent. So now, having said all of this, of course it would be natural to incorporate the entire spherical spectrum. Wouldn't it be wonderful if we have some multi-level sign rule which we eventually get to the 24 truths of unity instead of just dealing with plus minuses. So it seems very interesting, and at least in this area it's totally possible. I just don't have much time to discuss, so it would be very interesting to extend supersymmetry, supergeometry, to incorporate higher homotopy groups of spheres. So for instance, here the main concept is a symmetric monoidal category, where V tensor W is identified with W tensor V. So there's a categorification of commutative algebras in the ordinary sense. So we can imagine that V tensor W is identified with some categorical minus of W tensor V. And that's actually not really hard to set it up. So if the first step would be so that's called supersymmetric monoidal category. have a concept of supersymmetry. When V tensor W will be identified, not with W tensor V, but some twist, some, let's say, shift of parity to something. W tensor V. Well, in principle, one can continue, and this is clearly a very interesting subject to think of. Thank you very much.
Thank you. So, any questions?
This is a very interesting talk. Many questions that I would like to ask you, but one maybe simple-minded question is a cumulative, there is a notion of a two-ring, which is really a molecular category where, in addition to having the molecular structure, you may have some colimit, and the tensor product would preserve the colimit. I'm thinking of the colimit as sums.
Yes.
So one could try to do algebraic geometry with two rings, with these cumulative two rings.
Yes. So what's a bit interesting would be to look at commutative objects in commutative two rings. That would be like more. So yes, so commutative two ring should have commutative ring objects in which more familiar algebraic geometry would live. Yes, but what I'm thinking is more of something like this, which is so that the tensor product is not symmetric, it's not even braiding. When we look at something like this, it's not even braiding. But it's sort of analogous to supercommutativity. So again, I think that what you have in mind should be incorporated here. So here the assumptions would be that the category is linear over a field, there are direct sums, and it is distributive with respect to direct sums. So it's part of what you say about colimits. Yes, so yes, I think that should play a role, yes.
So it means that possibly extending this algebra or geometry, I don't know, would mean to have further level of higher categorical structure.
Yes.
Thank you.
Okay, other questions?
Do I understand right that the condition that exponent of the square root of the operation is local operator is necessary when you extend supersymmetry to the odd sector?
No, it's not necessary, and I don't think it has been noticed that exponentials of the supercharges are local. So what I said is in the simplest case, this relates to something which has been known for a while, but I don't think it has been noticed or used. Yes.
But you think it always will go in other cases, or?
Yes.
Thank you.
Just quickly related to what you're saying about taking just a linear envelope, for example, in the lowest dimensional case.
Yes.
Is there a formal notion of what that means?
Yes, I can tell you right now. I just was thinking whether to discuss it or not. So suppose I have a Picard-Duploid P, and suppose I have a homomorphism from pi 1 of P to K star. Then we can consider spaces graded by P. So we consider functions from P to that, in which the automorphism of objects is acted by this, right? And then there is a version of graded tensor product when you take the colimit in P. It will give you exactly this.
And just out of curiosity, is there a corresponding linearization?
Yes, if you get it like this, yes. Okay.
Maybe another question. In stochastic differential calculus, there is a square root of dt,
That I don't know. I know that the square of dt, but not the square root. I'm not aware of square root.
Square root of the differential dt.
Okay, so then it's something I want to learn.
Okay.
I don't know. I remember there is a dt square, but that, yeah, but it seems right, yes, for Brownian motion, there's something of order 1/2. Yes, it's something I want to learn. Yeah. I don't know.
But this is hard density, so it's hard density.
Ah, it's hard density. Oh.
It's density, yeah.
No, that's understandable. But what I understand, remember, in the ether formula for transformations of stochastic integrals, there are extra terms. Yes.
When in the beginning you said that there is nothing essentially apart from supergeometry, usual one, it was not quite right. So the sense of that was that still extension was
Yes, so what I had in mind.
Something
Yes.
new.
Yes, what I had in mind.
Something else.
Yes. But in the old days, there were of supers, there were attempts to extend, to play with other cycles. And it ended up by a theorem, I think it's called Nekludova theorem, in the seminar on supergeometry, that nothing like this is possible. No matter what you do, eventually there will be some overall grading, and you will end up doing causal sign rule with respect to this overall grading. So mathematically, this corresponds to the fact that the free Picard will poison one object. So to describe it is this. But if you introduce multi-level things, it seems to be a different direction. So here, further things should be possible.
Do you have an idea of, on the physical level, such an extension, what could mean? I mean,
well, here we somehow we're already bombarded by 24 truths of unity about the lattices, about Niemeyer lattices of order 24 lattices, other than Leach lattice, about the conformal weight modulo 24 in conformal field theory. So there is something like, I want to say something like this. So here, one of the way of getting this Zimmer 2 is as the Super Brouwer group of CTC Wall. There was a work of Wall in 1960s of So it is the same group. So there are two types of simple superalgebras. There are matrix algebras, and there are so-called queer superalgebras. Matrices type M and type Q, and they correspond, it was found well before interest in supers. So here one can think about the categorical analogues of superalgebras, of various modular categories, monoidal categories of this nature, should possibly be organized into something which will map into Zimmer 24. So here, of course, it's extremely appealing to incorporate all of this into some kind of unified super theory.
Other questions? Well, if not, let's thank the speaker.